In Chapter 3, we focus mostly on trying to find derivatives, working on different derivative rules, working with different types of functions. In Chapter 4, we're going to try to get as much information as we can out of the derivative. So we're much more focused on what can we do with the derivative now that we know how to take the derivative of all of these different functions. And we're going to start with this idea of maxima and minima, and we're going to start just by defining what those are. So here, let D be any set containing a point C. So D is just some set, you can think of it as an interval for right now, containing an x value of C. If f of C is greater than or equal to f of x for every x in your set D, then f of C is an absolute maximum of f on that set or on that interval D. So essentially, this is a fancy way to say that f of C is the highest point in the domain. So when you look at your graph, if you were to look at your graph, f of C, that's going to be the highest point of your function over whatever set we happen to be talking about. So here, this would be my absolute maximum here. It's just the highest point. If f of C is less than or equal to f of x, and actually let's do this in red. If f of C is less than or equal to f of x for every x in D, then f of C is an absolute minimum of f on D. So this is just a fancy way to say that this is the lowest point of our domain. So here, if I look over at the graph that I've drawn on the right, here, this point looks like it's going to be the lowest point of my domain, so that would be my absolute minimum, this point right here. An absolute extreme value, if we ever talk about extreme value, it's either an absolute maximum or an absolute minimum. Some of these problems, eventually we're going to be concerned with finding extreme values. We're going to want to go in and find those. So a lot of times problems will say, go find the absolute extreme values, which really just mean go find the absolute max and go find the absolute min. And I really want to focus here on just imagining and gaining an understanding for what absolute extreme values or absolute extrema look like. That's another term for absolute extreme values. And it really depends on the function and whether your interval that we're talking about, usually we're working on an interval, it matters what that function looks like, and it determines on that interval whether that interval is open or closed. So if I start with part of a parabola, let's say my function looks something, let's say my function looks something like this here. If I look at this function, I would say, okay, at this point right here, this is the lowest point of my function. This is my absolute minimum. And the highest point, that looks like it's the left endpoint over here. This is my absolute maximum. So that one's kind of a nicer function to work with. We begin to have problems if we're working with, say, an open interval. So let's draw that exact same function, but this time I'm not going to include the endpoint. So I'm not going to include the left endpoint and the right endpoint. So here, if I said find the absolute extrema of this function, well, this part right here, that's still the lowest point. That is my absolute minimum. But I run into a problem because the highest point should be this open circle. But I can't take that open circle as my absolute maximum because that point is not in my domain. The function does not exist at that open circle. And then so one fix that we might try is we might say, okay, what about, and I'm going to intentionally choose a point that's wrong. I'm going to say, what if we choose a point that's right here? Then what if that's the highest point? And I can say, well, we can always get a little bit closer. How about that? That point's higher. And then you might say, okay, well, how about that one? That should be our absolute maximum. But we can always get a little bit closer, and we can always get a little bit closer. Now, we're bound by the restrictions of how many pixels are on the screen, but hopefully we get an idea where as we move closer and closer, if I were to kind of, let me just draw this piece right here. I'm just going to try and zoom in on that. What we're essentially saying is, okay, maybe I think this point right here and is my absolute maximum, but I can always get a little bit higher. I can choose this point right here, and then this point right here. And then, okay, we need to zoom in further. So we pick this point right here, and we continue this process forever and ever, right? You can just keep zooming in infinitely. You can get infinitely close to this open circle right here, but you're never going to pick a highest value, because you can always get a little bit closer to that open circle. So this particular function, kind of interesting, this has no absolute maximum. And it's because we live on this open interval. Because there is no highest point. If you pick a point and say, I think that's the highest point, I can always just get a little bit closer, and I can always find a point that's just a little bit higher. So there is no absolute maximum of this particular function on this particular interval. Things get even worse if we work with functions that are perhaps not continuous. So if I drew something that was on that open interval, or actually here, let's do this. Let's live on a closed interval, so we'll contain the endpoints, but this time I'm going to have a hole, and I'm going to place the hole right there. So here, we're going to run into a lot of the same problems that we just did. We can say, okay, we have this point now. This is our absolute maximum, so we fixed that problem, but now we have this hole right here, and we're going to run into the same problem with our absolute minimum that we did with our absolute maximum. So you can always just get a little bit closer, get a little bit closer. In this case, we're going to find a y value that's just a little bit lower and a little bit lower. So in this case, we will have no absolute minimum here. So if we want to eventually be able to find these absolute extrema, because that's what we want to be able to do, is we want to be able to find these absolute extreme values. We're going to do that by the end of this section. We first need to make sure that we actually have an absolute maximum and an absolute minimum to find. So we need some way to guarantee that we have these points to find, because otherwise we're looking for something that just isn't there. So here's where the extreme value theorem is going to come in. This is a named theorem, so I think this is a pretty important one. This could be one that I ask about. It says a continuous function. So here we're solving the first problem, right? Or excuse me, the second problem. Our function needs to be continuous, which means we can't have any holes, we can't have any asymptotes, we can't have any breaks in our function, nothing weird like that. So our function has to be continuous on a closed interval, and this solves our other problem of not containing the endpoints. That solves this issue that we were having up here. So we're saying, okay, you need to contain the endpoints of your interval. So we need to contain both the left and the right endpoint. And that's what this notation right here, remember that when we use brackets right here, that left-hand bracket says A is included in the set, the right-hand bracket says that B is included in the set. So if we have a continuous function on a closed interval, it is guaranteed to have an absolute maximum and an absolute minimum on that closed interval AB. So this is the first way that we can guarantee ourselves absolute extreme values, is we need a continuous function and we need to be working on a closed interval. So first up, we're just going to look at some examples here and just pick out those absolute maximum and minimum values. So here we want to identify the location of the absolute maximum and absolute minimum values on the interval AB. Do the functions meet the conditions of the extreme value theorem? So here I just want to practice picking out what's the highest point and what's the lowest point. So for part A right here, this point right here I want to talk about in particular because I can anticipate some confusion about that point. Some students might pick that and say, well, I think that's the highest point. That's an absolute maximum. And I'd say, well, you're kind of right. You're right in that it's a high point. It looks like it's higher than all of the other points around it. But remember, we're only concerned with the highest point. Do we have a highest point right here? So here in this case, we do have a point that's higher. I can take this point over here. This is my absolute maximum. So this point, it turns out it is going to be important, and we'll talk more about it later. But for right now, if we're just focused on absolute extreme values, that is not an absolute extreme value. And then right here, that lowest point, sort of the vertex right here, this appears to be our absolute minimum. And then the question that's asked here is, do the functions meet the conditions of the extreme value theorem? Well, in this case, we're checking two things, right? We're checking, is it continuous and is it on a closed interval? So here we have a continuous function. There are no holes, there are no breaks, there are no asymptotes, nothing like that. So it's continuous, and we contain the endpoint. So we're working on this closed interval. So yes, it meets the conditions for the extreme value theorem. So we'll say yes, it meets the extreme value theorem. And we can tell that because we are guaranteed to have an absolute maximum and an absolute minimum. So over here in B, I've drawn very much the same graph, a very similar graph, only this time we don't contain those endpoints. We're not containing the left or the right-hand endpoints. So what does that mean? Well, we said that this point right here was our absolute maximum. We're going to run into problems here because our function doesn't exist there. And we can't pick that highest point because, remember, we can keep zooming in on that. We can keep getting a little bit closer and a little bit closer. So in this case, I have no absolute maximum. I can't pick an absolute maximum because there is no single highest y value here. And actually, just by determining this, no absolute maximum, if we don't have either an absolute maximum or an absolute minimum or both, that automatically means that we do not meet the conditions of the extreme value theorem, because the extreme value theorem guaranteed that we had both of these two. And I just said, well, I don't have one of those two. I don't have that absolute maximum. So this does not meet the conditions for the extreme value theorem. However, just because it doesn't meet the conditions of the extreme value theorem doesn't mean that I don't have an absolute extreme value. I may still have an absolute maximum or an absolute minimum or both. The extreme value theorem is just a way to guarantee us. So it's possible to have an absolute extreme value while still not meeting the conditions for it. So if I look right here, this point remains kind of unchanged. This is still my absolute minimum. So I can still have an absolute extreme value even though I don't meet the extreme value theorem. The extreme value theorem is just a way, again, to guarantee that we have both an absolute maximum or an absolute minimum. All right, so now we're going to talk about those other points. So suppose I is some interval containing a point C, so here C is an x value again. If f of c is greater than or equal to f of x for all x in your interval I, then f of c is a local maximum. So here this is just, I'm gonna call this a high point. So it's not necessarily the highest point, it's just a high point compared to the other points that live around it. And then alternatively, if we switch the direction of the inequality, if we say f of c is less than or equal to f of x for all x in your interval I, then f of c is a local minimum. Again, this instead is a low point. Not necessarily the lowest point, although it could be. It could be the lowest point, but it's just a low point. So in this example, I just want to look at the graphs here to identify where we have local extreme values and where we have absolute extreme values. So we're picking out our highest points and our lowest points here. So I'm going to start by working with, I think, the absolute extreme values. We're a little bit more familiar with those. What's the highest point of our graph? Well, it appears to be right here. This is my absolute maximum. And then I have some other low points right here, although it looks like I have 2 points which are tied for our lowest y value here. Those are about the same y value, it looks like. So if that is the case, if that happens, we're going to say that both this point and this point are the absolute minimum values. Because remember that the absolute minimum values refer to, when we say an absolute minimum, we're really referring to the y value. And if they have the same y value, well then sure, yeah, it's the same y value that we're really talking about. It just achieves that y value in 2 different locations on our graph. So at this point, we've identified our absolute extreme values. We should also talk about our local extreme values. So we're looking for a high point and a low point compared to the points that are around it. So in this problem, I'm going to take this point right here. This point seems to be lower than all the other points around it. This is lower than if I kind of make my interval here and here, if I kind of just compare this point to all the other points around it. That is lower than everything else. So it's an absolute minimum, yes, but it is also a local minimum as well. So you can have points be both absolute and local extrema. We can have that happen. This point right here looks like it's a high point, so in this case we would say that that is a local maximum. It's not an absolute because it's not the highest y value there. On the next graph, part B, we'll start again by identifying those absolute extreme values. I'm going to pick the lowest point, which it appears is right here. Here is my absolute minimum. This point right here looks like it's my absolute maximum. And then I also want to be able to pick out any local extreme values. So I have a point, let's say, actually, let's even just start right here. This is a high point. It also happens to be the highest point. This is also a local maximum. So it is a local and an absolute maximum. This point right here looks like it's a low point compared to the points that are around it. If I kind of look at that particular section of my graph, that seems to be the lowest point of that particular section. So this is a local minimum. And then this point right here, this appears to be a local maximum here. It's higher than all of the other points around it for that particular section of the graph. So this is a local maximum. This point right here, in this case, is our endpoint. Right now, we are going to say that endpoints are not going to be local extreme values here. It's possible that it might be an absolute extreme value, but for now, when we're on these closed intervals, we are not going to say that endpoints are local extrema. We want to save those for points in the middle of our graph, what are called interior points of our graph. So hopefully this clears up some of the differences between local and absolute extreme values. In the next video, we're going to talk about how we might go about finding some of these values.